Alright, so this is the second part of the Honors Chapter 17.1 lesson video. And so just remember that to get all my videos in one place, you can just subscribe and then you'll have them easily available to yourself. So anyway, let's pick up where we left off. So of course, this was our chapter on thermochemistry. So we're just going to continue. So we learned, how to do calories and joules and that type thing in the first video. So let's go ahead and finish up the chapter. The section, not the chapter. Boy, I'm making a lot of mistakes today. I'm sorry. So the first thing is the first law of thermodynamics. So the first law of thermodynamics states that energy is conserved. So it can be changed in other forms, but overall, the total amount of energy must remain constant. So energy can transform from one form to another, or it can move to different places. But the overall energy must remain constant. So, kinetic energy could turn into heat energy, or, one particle could lose kinetic energy to another particle, but overall energy must remain constant. So let's talk about internal energy. The internal energy, represented by E of a system, is the sum of all kinetic and potential energy of its components. So calculating E by itself is kind of difficult, but to calculate change in E, which remember delta just means change in, is easier and more useful. And of course our change in is our final energy minus our initial energy. So delta E can be positive or negative. If it's positive, then the system has gained energy, and remember we discussed that that is unfavorable. And if delta E is negative, that means the system has lost energy, and that's a more favorable situation. So if you were have a question about which reaction is more likely to occur, and you knew one had a positive delta E and one had a negative, then the negative delta E would be the one that would be more likely to happen. So delta E, we won't really use the E final minus E initial often, but we will use Q plus W. So Q is heat and W is work. We already talked about work in the last video. It's force times distance. So when heat is added to a system or work is done on a system, its internal energy increases. So work being done on a system or by a system is usually a change in volume. So if a system expands, it does work on the surroundings. If a system contracts, we say the surroundings do work on the system. And then of course your Q is your heat. So I think we can all tell whether or not that's going into or out of the system. I hope you can tell. So this is a super long question with a really simple answer. So it says two gases, A and B, are confined in a cylinder and piston arrangement like that in figure 5.3. Well, that's convenient. I don't have figure 5.3 to show you, but clearly it's just a cylinder with the piston and the gases inside. Substance A and B react to form a solid product. So we have gaseous A and B reacting to form solid C. As the reaction occurs, the system loses 1,150 joules of heat. Okay, so notice the system loses this much to the surroundings. The piston moves downward as the gases react to form a solid, as the volume of the gas decreases under the constant pressure, because of course as these gases form a solid, it doesn't take up as much room. So that piston would be able to lower or move downward. Under constant pressure of the atmosphere, the surroundings do 480 joules of work on the system. Okay, so the surroundings do this much work on the system. What is the change in the internal energy of the system? So see, this was a long question, so that all we can do is plug into delta E equals our Q plus our work. All right, so let's look at what's happening. We just need to determine the signs. So it says the system loses 1,150 joules. So for my Q, since the system's losing that heat, I'm going to put negative 1,150 joules, okay, because it's losing it. And then it says the surroundings do 480 joules of work on the system. That means the system has that work done on itself. So I'm going to add the work that the surroundings did on the system. And so when I combine those, I end up with negative 670 joules. Okay, so all you have to do is decide whether Q and W are positive or negative. So if the system loses heat, it's a negative number. If the system absorbs or gains heat, it'll be a positive number. If the surroundings do work on the system, it's a positive number. If the system does work on the surroundings, it's a negative number. So that's all you really have to know for these type questions. Okay, so let me let you try one real quick. So, y'all try this one, just pause it, try it on your own, and now we'll do it together. So, calculate the change in the internal energy of a system for a pressure in which the system absorbs 140 joules of heat from the surroundings and does 85 joules of work on the surroundings. So in other words, this time the system's doing the work. Okay, so remember, our delta E equals our work plus our heat, or our heat plus our work. So since it's absorbing 140 joules, that means that's coming into the system. I'm going to keep my heat as positive. And then here, though, it says, and does 85 joules of work on the surroundings. That means I'm going to do a negative 85 joules because that work is going to the surroundings, not going to the system. All right, and so once I solve, I got 55 joules. So hopefully you got that right. Nothing really tricky about this formula, just make sure you have your positives and negatives right. Okay, so let's move on. The section's super long, so the easy stuff I'm going to try to do really fast. Alright, so state function is a property of a system that is determined by the system's present state and not affected by the path taken to get there. So your delta E, or your internal energy change, is a state function. So for example, it says 50 grams of hot water cooling to 25 degrees Celsius versus 50 grams of ice warming to 25 degrees Celsius. Well, here we're starting with hot water and it's going down in temperature, but it ends at 25 degrees Celsius. Here we're starting with ice, which is cold, and it's warming up to 25. But in both cases, they ended up at 25 degrees Celsius. So it doesn't matter how we got there. Another example is if you look at this parking deck, we're trying to get from the bottom to the top. In this case, a man pushes the car up and up and up each ramp to get it to the top. In this case, somebody rides the little lift that takes you all the way up. Did they both end up on the top? Yes. So it didn't matter how they got there. Now, the weird thing is, Q and W, though, are not state functions, and that's what we add to get our delta E. Because who did more work in this case, this man or this guy? This man did more work because he had to push that car up the ramp, whereas this guy, he just used the lift. All right, so that's what a state function is. We're not worried about the path taken. So here's just a little bit more about energy and some definitions. So energy is the capacity to do work or supply heat. We already said that. Energy has no mass or volume, so it is not a form of matter. Chemical potential energy is the energy stored in chemicals within the bonding arrangement. And then the kinds of atoms and the arrangement of the atoms in the substance determine the amount of energy stored in the substance. So we'll look at different calculations involving heat changes and energy changes, and a lot of times the numbers change based on what the substance is. So heat is a form of energy that always flows from a warmer to a cooler object. We talked about that in the previous video. Heat is represented by Q. Yes, I know that's weird, but H is already taken. Capital H is enthalpy, which is related to heat. We'll talk about that later. And lowercase h is Planck's constant, which we already did back in chapter 5. Okay, so heat is Q. So thermochemistry is the study of heat changes that occur during chemical reactions and physical changes of state. We'll talk about how to calculate your heat change in both instances. So we have to follow the law of conservation of energy, which of course, like every law of conservation, it says whatever is at the end cannot be created nor destroyed in any chemical or physical processes. All right, and that's exactly what this says right here. So our energy overall in the universe must remain the same. Remember, it can change forms, it can change locations, but it can't be created or destroyed. So, we talked about calorie in the previous video, and calorie is the amount of heat required to raise the temperature of 1 gram of pure water 1 degree Celsius. So next we're going to talk about two definitions that are very similar to that. So heat capacity of an object is the amount of heat it takes to change an object's temperature by 1 degree Celsius. So notice we didn't specify what the object was. Like in calorie, we said it had to be water. And we didn't specify how much of the object. In calorie, we said it had to be 1 gram of water. So the greater the mass of the object, the greater the heat capacity. And the heat capacity also depends, of course, on chemical composition. So in other words, like when we think about heat needed to increase it by 1 degree Celsius, think about this. I can increase a glass of water by 1 degree Celsius using like a Bunsen burner for just a couple seconds. Whereas if I put a Bunsen burner underneath an entire swimming pool, I'm not going to change it by 1 degree Celsius for a while. It will probably take more than one Bunsen burner because there's a lot more water here. Okay, so heat capacity is based on how much you have. Now, specific heat capacity is the other one that's very similar. A lot of times you'll just hear it referred to as specific heat. People drop capacity. So the specific heat capacity of a substance is the amount of heat it takes to raise the temperature of 1 gram of the substance 1 degree Celsius. So here's the difference. Heat capacity, we're raising something by 1 degree Celsius. Specific heat capacity, we're raising 1 gram of something 1 degree Celsius. Calorie, we're raising 1 gram of water 1 degree Celsius. So they're very similar, but there are those differences. So specific heat capacity or specific heat is represented by a C. So if you remember capacity and C. The units for specific heat are joules per grams degrees Celsius. However, sometimes you'll see joules per gram Kelvin, and it actually doesn't matter which one you use. They can be used interchangeably here, and the only reason why is because we're looking at a change in temperature when we talk about heat. And so a change in Celsius and a change in Kelvin are the same thing. So say I go from 0 Celsius to 100 Celsius. That's a change of 100 degrees. Well, 0 Celsius is 273 Kelvin. 100 Celsius is 373 Kelvin. So 273 to 373 is also a 100-degree change. So just keep in mind, you may use those interchangeably for this chapter. So don't do that in gas laws, though. We all talked about that. All right, so water has a higher specific heat than most substances. So in other words, if you look here, these are the same mass of different metals. They're different sizes because, of course, we need the same amount of moles, and so the mass is going to be different. They heated them to the same temperatures, and then this is a giant block of wax. And so they put them at the top and allowed them to lose their heat and melt as much wax as it could and lower. And so if you look, even though they were all the same temperature to begin with, some of them held more heat than others. Okay, so that shows that difference in specific heat capacity. So our next formula is heat, which is Q, equals mass times specific heat capacity times delta T, which is change in temperature. So mass is going to be in grams, okay, has to be in grams. Now remember, when we talk about energy, it has to be in kilograms. Specific heat is joules per grams degrees Celsius or Kelvin. And then change in temperature is usually in degrees Celsius, but you'll see Kelvin also. And remember, it doesn't matter which one you use because the change will be the same. So let's look at the first sample problem, and let me get to the correct page because I'm just flying through these slides. Hopefully this video won't be too long, but we'll see what happens. So it says the temperature of a 95.4 gram piece of copper, so there's my mass, increases from, whoop, that should say from. Y'all know I got typos and everything. That should say from, we'll fix it right now. From 25 degrees Celsius to 48 degrees Celsius. Okay, so here is my initial temperature, here is my final temperature. When the copper absorbs 849 joules of heat, so there's my Q, what is the specific heat of copper? So in this case, I'm actually looking for C, my specific heat. All right, so we know Q equals MC delta T. So if I solve for C, I have to divide by M and delta T. And then I'm ready to plug in. So I have my Q, which is 849 joules. I have my mass, it's in grams like it's supposed to be. It's 95.4 grams. Now we got to do our change in temperature. Okay, so delta T, or your change in temperature, is your final minus your initial. It's not always necessarily largest minus smallest. You can have a negative temperature change if it is cooling down. Okay, so in that case, I would do 48 minus 25, and that gives me 23 degrees Celsius. And then I can plug that in right here. So once I do my math and I divide by those numbers in my denominator, I ended up getting 0.39. And then if you look, a joule, a gram, and a degree Celsius, none of those will cancel. So I'm left with joules per grams degree Celsius. Just like that. Okay, your specific heat will always have 3 units like that. Alright, so hopefully you didn't think that was too bad. So let me let y'all try some, so that way we can make sure you know what you're doing. Alright, so y'all try this one, so just pause the video and then of course check your answer with me. So we'll do it together now. when 435 joules of heat, so there's my Q, is added to 3.4 grams, so there's my mass, of olive oil at 21 degrees Celsius, so there's my initial temperature, the temperature increases to 85 degrees Celsius, so there's my final temperature. What is the specific heat of the olive oil? So again, we're looking for C. All right, so I have Q equals MC delta T. I'm looking for C again, so I divide by my M and delta T. And then I'm ready to plug in. So my Q is 435 joules. My mass is in the correct unit again, 3.4 grams. And then we got to get that delta T. All right, so my delta T, of course, is 85 minus 21, which gives me 64 degrees Celsius. So then I plug in that 64 degrees Celsius in the denominator. And then when I solve, I got 1.99 joules per grams degrees Celsius. All right, so hopefully you got that one right. Nothing tricky there, no converting. I know you are probably like, oh my God, what? But yes, there was no converting on this one. All right, so let's look at another one, I think is what's next. All right, so again, y'all try this one real quick. Pause it, try it, and let's do it together. So it says how much heat, so this time we are actually solving for Q, is required to raise the temperature of 250 grams, so there's my mass, of mercury, 52 degrees Celsius. Now notice they only gave me one temperature, but they said required to raise the temperature 52 degrees Celsius. So here they actually already gave me delta T. I don't have to figure out what it is. And then they tell me specific heat of mercury is 0.14 joules per grams degrees Celsius. So there's my C. So in this case, you didn't even need to rearrange the formula. So Q equals MC delta T, so I just plug in. So my mass is in grams like it's supposed to be, 250 grams. My specific heat is 0.14 joules per grams degrees Celsius. And my change in temperature is 52 degrees Celsius. So if you look, degrees Celsius cancel, grams cancel, I'm left with joules. And so then when I multiplied, I got 1,820, and my unit, of course, was joules. All right, so hopefully you got that one right too. So just be careful. Sometimes I will give you delta T, not your final and initial where you have to subtract. So hopefully you found that formula pretty easy. Basic algebra, so you know it shouldn't be too hard. All right, so section 1 assessment. Wow, this section just went faster than I was expecting. All right, so in what direction does heat flow between two objects? So remember, it always flows from warmer to colder, or hot to cold. So let's just say hot to cold. All right, always flows from hot to cold. So how do endothermic processes differ from exothermic processes? Remember, endothermic heat is coming in. So for endothermic, we can say it absorbs heat. And for exothermic, we can say it releases heat. Because remember, exo is, think of exit. So heat is leaving the system. So number 3, it says, on what factors does the heat capacity of an object depend? Well, if you remember, that was the cup of water and swimming pool water example. So one thing is mass. And the other thing was chemical composition. Remember, each type of substance will have its own numbers in this chapter. That's why if you just saw in the last question, mercury had its own specific heat. Olive oil in the previous one had a different specific heat because it has a different chemical composition. All right, so number 4 is a math question. It's Q equals MC delta T1. So it says how many kilojoules of heat are absorbed, so we're looking for Q, but remember when we solve for Q, we're gonna get joules. So we do need to make a note that we're gonna need to change it to kilojoules. All right, so how many kilojoules of heat are absorbed when 1,000 grams of water, so there's my mass, is heated from 18 degrees Celsius, so there's my initial temperature, to 85 degrees Celsius, so there's my final. And then I tell you the specific heat of water is 4.184 joules per grams degrees Celsius. All right, so let's go ahead and solve. So we have Q equals MC delta T. So let's plug in. So my mass is 1,000 grams. My specific heat is 4.184 joules per grams degree Celsius. And then we got to figure out our delta T. So of course delta T is going to be our final 85 minus our initial of 18, which is 55 degrees Celsius. Look, just kidding, I'm looking at the wrong spot. 67 degrees Celsius. Sorry, I don't do mental math, y'all. That's what calculators are for. All right, and so then I plug in my 67 degrees Celsius right here. So degrees Celsius and grams cancel, and when I solved, I got this right here, 280,328 joules. But the problem is, they want a kilojoules. You know, I'm always going to throw converting in there somewhere. Sorry, I personally love converting. We all know this. So 1 kilojoule equals 1,000 joules. It's just like 1 kilometer equals 1,000 meters, or 1 kilogram. Kilo always means the same thing. So 3 zeros means we move the decimal 3 places, or divide by 1,000. Okay, so my decimal is currently right here, so 1, 2, 3. So it will become 280.3 kilojoules. And I'm just going to drop those last 2 numbers. You can keep them if you want to. All right, so you just got to be careful of units. You know, I like to make you convert units. All right, so let's move on and knock out the last couple slides. Ooh, sorry, that took me a long time to erase. If I knew how to edit a video, I could cut all that out, but I don't, so oh well. So using calories, so I underlined it just to make sure you notice that. Using calories, calculate how much heat, so of course that means we're looking for Q, 32 grams of water, so there's my mass, absorbs when it is heated from 25 degrees Celsius, so there's my initial temperature, to 80 degrees Celsius, so there is my final temperature. How many joules is this? So in other words, we need to get joules and calories, so we'll have 2 answers. Specific heat of water, again, is 4.184 joules per grams degree Celsius. All right, so when we plug into Q, we're automatically going to get joules. So that would be one of my answers, and then I just need to convert that to calories also, which we learned that in the previous video, so we'll use that information. All right, so we're solving for Q, so we don't have to rearrange. So Q equals MC delta T. So I just start plugging in. So my M is my mass, which is 32 grams. My C is my specific heat, which is 4.184 joules per grams degree Celsius. And my change in temperature, let's figure out what that is real quick. It's final, which is 80, minus initial, which is 25. So that would give me a 55 degrees Celsius change in heat. I mean, not change in heat, sorry, change in temperature. So once I multiply all that, I got 7,363.8. Celsius cancels, grams cancel, so I'm left with joules. So notice, one question said, how many joules is this? There's my joules answer. But the original question said using calories. So let's just change it real quick. So I have 7,363.8 joules. So if you'll remember from the previous lesson video, 1 calorie equals 4.184 joules. So golden rule says 4.184 joules goes on bottom, 1 calorie goes on top. So joules cancel, and once I divided, I got 1,760 calories. So now we have our answer in joules, we have our answer in calories. All right, so just be aware that, you know, I combine problems sometimes. That's the thing that some of y'all have trouble with, is when I do combine problems. All right, so let's move on. Almost done, almost done. Alright, so number 6, it says how much heat is needed to warm 250 grams of water. So in other words, we're looking for Q again. And we have our mass, about 1 cup, from 22 degrees Celsius, so there's my T initial, to nearest boiling point, 98 degrees Celsius, so there's my final. The specific heat of water is 4.18 joules per gram Kelvin. Now notice, this time I gave you 4.18 instead of 4.184. Sometimes they'll give you specific heat and they don't put the 4. Sometimes they do. Now notice it changed to Kelvin, but we have Celsius. But remember, I told you it doesn't matter. The change in the 2 is the same. So you know what I like to do when they give me a problem like this is I'll just change this to degrees Celsius myself. And then that way I'll see that my Celsius will cancel. All right, so let's go ahead and plug in. So Q equals MC delta T. So of course my mass is 250 grams. My specific heat is 4.18, whoop, no 4 this time, 4.18 joules per grams degrees Celsius. And then let's look at that change in temperature. So remember, it's going to be my final, which is the 98, minus the 22, and of course that gives me 76 degrees Celsius. So my Celsius cancel and my grams cancel, and I'm left with joules. And so once I multiplied, I got 79,420 joules. All right, now the next one is one that throws a lot of people off in my class. In thermochemistry, sometimes if you'll just look at what type of units you need, it's not necessarily a plug into a formula question as much as it is transform units into new units. All right, so this says what is the molar heat capacity of water? So specific heat capacity is joules per gram degrees Celsius or Kelvin. Molar heat capacity is joules per mole degrees Celsius or Kelvin. Okay, so in other words, somehow we need to change the grams to the moles. So there's no formula to remember for this, it's just common sense. We know how to change grams to moles, we've been doing it since chapter 10. Okay, so our specific heat capacity for water is 4.18 joules per grams degrees Celsius. Don't worry about changing to Kelvin, you can put Kelvin if you want to. I just changed it to Celsius because they gave me Celsius in the problem. All right, so we need to change the grams, but the grams is on bottom. So golden rule says, where would I put it to cancel it out? On top. Well, what are we talking about? Well, we're talking about water. Water's molar mass is 18 grams, because when you add up H2O off the periodic table, you get 18 grams. So I just put 18 grams on top equals 1 mole on bottom. So if you look, those grams cancel, and see I'm going to have joules per mole degrees Celsius, which is what we would have for molar heat capacity. So once I multiply, I got 75.24 and then joules per mole degrees Celsius. Now like I said, you can put joules per mole Kelvin, that's fine, it doesn't matter because the Celsius and Kelvin is the change in them, and that is the same on both scales. Alright, so like I said, sometimes it's just about a unit conversion. Alright, I think there's one more slide. We'll finish this at some point. Let's see, is this the last slide? Yay, the last slide. Alright, so large beds of rock are used in some solar heated homes to store heat. Assume that the specific heat of the rocks is 0.82 joules per gram Kelvin. So we have a C. Calculate the quantity of heat absorbed, so we're looking for Q, by 50 kilograms of rock. So there's my mass, but remember, for heat formula, mass has to be in grams. Kilograms is fine for energy formulas, but for heat, it has to be in grams, so we're going to have to convert that. Of rocks, if their temperature increases by 12 degrees Celsius. So again, y'all, here, I told you the change in temperature. We don't have to figure it out. Now, since they gave me degrees Celsius here, I personally am just going to change this to degrees Celsius. You're more than welcome to just change that to Kelvin if you want, because remember, the change is the same. So let's knock out this part first real quick though, because of course we can't use mass in kilograms. So 1 kilogram equals 1,000 grams. So I would just need to multiply that number by 1,000 or move the decimal 3 places, but this time to the right. So I end up getting 50,000 grams. Okay, so once I know that, I can plug in. So Q equals MC delta T. So my mass is, we decided, 50,000 grams. My specific heat, they told me, was 0.82 joules per gram. I changed it to degrees Celsius. You could have kept it as Kelvin, it doesn't matter. And my temperature change is 12 degrees Celsius. So my Celsius, my grams cancel. So when I solved, I got 492,000 joules. Just like that. Okay, so you just got to be careful of those units that you're plugging in. Then it says, what temperature change, so in this case, I'm looking for delta T, would these rocks undergo if they emitted 450 kilojoules of heat? So there's my heat now. Okay, so what temperature change would it have to go on? So we don't have temperature change anymore, we're looking for it. We can keep the same C and the same M though from the previous part because it's the same amount of rocks and so they'll have the same specific heat. But this time we won't use the 12 and instead of solving for Q, we're going to plug in the 450 kilojoules. Now there's the problem though. In this formula, Q has to be in what? Joules. So let's fix that real quick. So remember, we're going to take it and go 1, 2, 3, or multiply it by 1,000. So that's going to be 450,000 joules. And so now I can plug in. All right, so we have Q equals MC delta T. We're solving for delta T. So what do? We divide both sides by M and C. So delta T equals Q, which we decided is 450,000 joules. Because remember, can't use kilojoules. All right, and then, whoa, my line is terrible. Sorry about that. Boop. All right, and then we put our mass on bottom, which we decided our mass was 50,000 grams in the previous part, times our specific heat, which it told me was 0.82 joules per gram degrees Celsius. So in this case, my joules and my grams cancel, and I'm left with degrees Celsius or Kelvin. Okay, it doesn't specify which unit I have to use. I'm using degrees Celsius. You could easily say Kelvin. It doesn't matter. And so once I divided by that denominator, I got 10.98 degrees Celsius. Or, like I said, you could have put 10.98 Kelvin. Remember, a change in degrees Celsius or Kelvin is the same. Okay, now I'm not saying Celsius equals Kelvin. We know Kelvin is Celsius plus 273, but the change in the two is the same. All right, so hopefully that helped you with section 17.1, and then if you need to, you can look for my section 17.2 video coming soon.